Find the Maclaurin series for f of x equals sine of pi divided by 2x. Assume that f of x has a power series expansion and that Rn of x, the remainder, approaches 0. Then determine the radius of convergence. The formula for the Maclaurin series is shown below, which is the same as the Taylor series, centered at 0. To determine the Maclaurin series, we'll find the first several terms of the Maclaurin polynomial using the right side of the equation, and then hopefully recognize the pattern that we can use to write the formula for the Maclaurin series. To find the terms of the Maclaurin polynomial, we'll begin by determining the first several derivatives of the given function. Let's find the first three derivatives. Beginning with f of x equals sine of pi divided by 2x. Notice to find the derivative, we need to apply the chain rule. The first derivative is cosine of pi divided by 2x times the derivative of pi divided by 2x, which is pi divided by 2. F prime of x equals pi divided by 2 times cosine of pi divided by 2x. And now we differentiate the first derivative to find the second derivative. The second derivative is equal to pi divided by 2 times negative sine pi divided by 2x times another factor of pi divided by 2. The second derivative is negative pi squared divided by 2 squared times sine of pi divided by 2x. And now we differentiate this function to find the third derivative, which is negative pi squared divided by 2 squared times cosine pi divided by 2x times pi divided by 2, giving us the third derivative equals negative pi cubed divided by 2 cubed times cosine pi divided by 2x. And now because we're looking for the Maclaurin series centered at 0, we evaluate these four functions at x equals 0. F of 0 equals sine 0, which is 0. F prime of 0 equals pi divided by 2 times cosine 0, which is pi divided by 2 times 1, or pi divided by 2. F double prime of 0 equals negative pi squared divided by 2 squared times sine 0, which is 0. F triple prime of 0 equals negative pi cubed divided by 2 cubed times cosine 0, which is negative pi cubed divided by 2 cubed. And now using the formula below for the Maclaurin polynomial, here are the first four terms. Now we substitute in the function values we just found, which gives us t sub n of x equals 0 plus pi divided by 2 times x plus 0x squared minus pi cubed divided by the product of 2 cubed and 3 factorial times x cubed, and so on. Simplifying, we have t sub n of x equals pi divided by 2x to the first minus pi cubed divided by the product of 2 cubed and 3 factorial times x cubed. Following this pattern, notice the next term would be plus pi to the fifth divided by the product of 2 to the fifth and 5 factorial times x to the fifth, and so on. And now let's analyze the terms to determine the pattern to write the Maclaurin series. Notice the exponents on pi are 1, 3, 5, and so on, which also match the exponents on x. In the denominator, we have powers of 2. We have 2 to the first, 2 to the third, 2 to the fifth. And then analyzing the factorials, we could include a 1 factorial in the denominator of the first fraction. And now the factorials are 1 factorial, 3 factorial, and 5 factorial, which means if we ignore the alternating sign, and for sigma notation, begin with n equals 0, the formula would have to include pi to the power of 2n plus 1 and x to the power of 2n plus 1 in the numerator, and the denominator would include 2 to the power of 2n plus 1, as well as 2n plus 1 factorial. And then for the alternating sign, we include negative 1 to the power of n. This would be the Maclaurin series, where n starts at 0. If we start n at 1, this would be the equivalent formula for the Maclaurin series. We'd have the sum from n equals 1 to infinity of the product of negative 1 to the power of n minus 1, pi to the power of 2n minus 1, and x to the power of 2n minus 1, and the denominator would be 2 to the power of 2n minus 1 and 2n minus 1 factorial. But we'll go ahead and use the first formula for the Maclaurin series and now determine the radius of convergence. Let's do this on the next slide. To find the radius of convergence, we'll apply the ratio test, which means we'll determine the limit as n approaches infinity of the absolute value of the quotient of a sub n plus 1 and a sub n, which to converge must be less than 1. We begin by determining a sub n, which is the given formula, and then a sub n plus 1, and now set up the limit. we have the limit as n approaches infinity of the absolute value of, again, a sub n plus 1 divided by a sub n. Let's write this quotient as a product. Instead of dividing by a sub n, let's multiply by the reciprocal of a sub n. And now let's begin to simplify. Because we're taking the absolute value, the negative ones really don't matter, but negative 1 to the power of n plus 1 divided by negative 1 to the power of n simplifies to 1 factor of negative 1 in the numerator. Pi to the power of 2n plus 3 divided by pi to the power of 2n plus 1 simplifies to 2 factors of pi in the numerator. So we have a pi squared in the numerator. Similarly, x to the power of 2n plus 3 divided by x to the power of 2n plus 1 simplifies to x squared in the numerator. And now looking at the bases of 2 to the power of 2n plus 1 divided by 2 to the power of 2n plus 3 simplifies to 2 factors of 2 in the denominator. And 2n plus 1 factorial divided by 2n plus 3 factorial will simplify to 2n plus 3 times 2n plus 2 in the denominator. If we begin to expand 2n plus 3 factorial, we have 2n plus 3 times 2n plus 2 times 2n plus 1 and so on. Notice the factors of 2n plus 1 and so on would be equal to 2n plus 1 factorial. So now we can write the simplified limit as the limit as n approaches infinity of the product of negative 1 pi squared and x squared divided by the product of 2 squared, 2n plus 3, and 2n plus 2. Now determining the limit, notice as n approaches infinity, the denominator increases without bound, the value of the fraction approaches 0, and therefore the limit is equal to 0, which is always less than 1, which indicates the series converges for all values of x, and therefore the radius of convergence approaches infinity or equals infinity. So again, the series converges for all real values of x, and therefore the interval of convergence would also be all real numbers, which would be the open interval from negative infinity to positive infinity. Before we go, let's look at the graph of the original function, as well as the graph of the first several terms of the Maclauring polynomial. In red, we have the graph of the given function f of x equals sine of pi divided by 2x. And now in blue, we'll graph the first 3 terms of the Maclauring polynomial. And notice the Maclauring polynomial is an excellent approximation for the function around the point 0, 0. In fact, because the series converges for all real numbers, as we add more and more terms to the Maclauring polynomial, it would perfectly match the given function. I hope you found this helpful.